Okay, anyway, so I guess we can start now. Um, I
Yeah,
will I will not be checking the chat or anything. So if there are any questions or interruptions, just speak up. Don't no need to raise the hand or anything because I won't be seeing what is going on. So okay, so basically on the agenda today is discussing a paper by Greg Dresden from 2021 titled Fault-Free Tilings of a 3x rectangle with squares and dominoes, and we are going to do exactly what is written. We'll be enumerating we'll be finding basically the number of fault-free tiling of a 3x rectangle. So basically we are going after a sequence right now. So the layout and the planning is very simple. We first introduce some of the notions um, and concepts which we'll be using throughout the uh, presentation, and then we lay out some machinery and methods which we'll be using to tackle the two different problems. And then we first enumerate the number of the vertical fault-free tilings and then the completely fault-free tilings. So that is it. So getting started, first of all, to get everyone on the same page, a completely fault-free tiling of a board is a tiling with no vertical or horizontal faults, and so it is something which can, let's say, look like this. So if a tiling goes like this, then we see that there is a clear fault here no matter what is going on after this. So this is what a fault is, and let's say a fault free tiling would look something like this. So this is example, or at least a segment of a fault free tiling where there are no faults. So there are basically no horizontal, there is one horizontal line, there is one horizontal fault here, but there are no vertical faults. So this is what being vertically or horizontally fault free means. And we'll be finding a fourth order recurrence relation for the number of such tilings, and we denote the number of such tilings by un and vn respectively. Un denotes the number of the number of completely fault free tilings, and vn denotes the number of vertical fault free tilings of the 3 cross n board at hand. Okay, so just to get started, this is a 3 cross 6 tiling with both horizontal and vertical faults. So this is the first example, and this is a 3 cross 6 tiling, the same board with no faults. So there are no vertical faults, there are no horizontal faults, and this is one of the examples that we will look at near the end. So okay, first up, we get some initial values because we will be looking at some of the recursions and all that. uh, so so first of all, let's look at some initial values of u and v for n equals 1 and 2. We can just list them out there, it is not very difficult. So this is for n equals 1. We can see there are exactly 3 tilings, and all of them are of course vertically fault free because there is no scope for any vertical fault. So, and these of course have horizontal faults, so it is not possible to have v1 positive and v1 is equal to 3. Similarly, we can draw out for n equal to 2, and again we cannot have any completely fault free tilings, so they have to have some horizontal faults, and these are all the 13 uh, different tilings which are vertically fault free. So v2 equals 13 and u2 equals 0. And now for n equals 3 and 4, we can also get ahead of us and look at some of the tilings. You can see that we have drawn two tilings corresponding to u3 and u4, and those are basically the only two tilings possible. And as you can see, there is a nice symmetry, nice reflection of symmetry between these tilings. So from these examples, we can start to notice that u3, all the values un are even. So eventually, when we get to that, we'll be considering only the half values of un. So only a certain kinds of tilings, which we denote by tn. But anyway, I'm getting ahead of myself. So anyway, it is known that v3 equals 26 and v4 equals 66, but we can worry about that later on. So these are the uh, 3 cross 3 and 3 cross 4 completely fault free tilings. Now we consider some of the important issues that will addressing which will lead us to discuss some lay the foundations of the machinery that we'll be using. First up, for any tiling to be vertically fault free, we cannot have any basically any vertical tile in the middle. That being, if there is any vertical tile in the middle, then there has to be some kind of a horizontal tile above it or a square above it. And as we can see, in any of those cases, we'll have at least one fault to the right of it, to the left of it, on, or even worse, on both sides of it. So we cannot have any vertical tiles in the middle of the tiling. So the only vertical tiles that can appear only at the ends. So, and secondly, if it has to be horizontal fault free as well as vertically fault free, then not only the vertical dominoes cannot be placed in the middle, but also we cannot have vertical dominoes. We have to have vertical dominoes in the ends, namely because if we only consider, okay, there is let's see. If we only consider some of the, let's see, the board is, let's say, up to this. If we only consider the horizontal tilings like this, then let's consider a tiling like this. Then if there is no vertical tile, then it is necessary that there will be there will be exactly like two horizontal faults. So to avoid those horizontal faults, we have to place vertical tiles somewhere, either here and here. We cannot place it both here and here, because then we are only covering one fault. So we have to place it here, or otherwise we can just flip this. We can just rotate this kind of, and not rotate this, but we can take the mirror image of this, and then we see that the vertical tiles can either go here and here. So okay, that is not very clear, but you get the point. So that is the thing. So these are the only two configurations which are possible if the tiling has to be horizontally fault free as well. And if the tiling has this configuration, then it is necessary that it has to be horizontally fault free. There cannot be any horizontal faults, because along this line we get an interruption here, and along this line we get an interruption here, and similarly here as well. So there is that. Now lastly, we define the last and most important piece of machinery that we'll be using, which is overhang profiles. So what is this? This is these are basically 6 images of when we look at any state or any stage of the tiling from left to right. We get at any stage, since there is no vertical fault, there has to be either one domino sticking out or 2 dominoes sticking out. We cannot have 3 dominoes sticking out, because then there will be 2 faults here and here. So depending on where the 1 or 2 dominoes stick out, we basically name those configurations A, B, or A3, A to F. And basically these are the most important things that we are looking at today. And all of these vertical pairs, the A and D, are kind of complementary, and this will be an important thing later on. Similarly, B and E and C and F are complementary kind of. So there is that. So having these foundations, we can start looking at the vertical fault free tilings of a 3x N board. So we already have established that we have the initial values V1 equals 3 and V2 equals 13. After that, we of course use the machinery we defined in the last slide. So AN is defined, AN through FN are defined to be the numbers of such vertical fault free tilings, such that there is an overhang profile of, let's say, A or A up to F respectively in the end. Okay, so just for examples, these are the initial values of A and C. So as you can see, this is a tiling of a 3x1 board, so just a vertical strip with an overhang of this domino A, and similarly this is another such tiling. And for a 3x2 board with an overhang of A, we can see there are 4 possibilities. And again, because C is exactly the mirror image of this, so we can get that for any tiling which is counted by AN, there is a corresponding tiling which is counted by CN. So CN of course equals AN, and just by flipping these tilings we see that C1 equals 2 and C2 equals 4. And similarly for B we can count, we get B1 equals 4. This is the only way to tile this stripe, this 3x1 strip, such that there is this B hanging out in the end. And these are the 5 possibilities of B2. So these are the 5 ways to tile. And among these we see that here are some tilings which are basically fault free. Okay, now having obtained the initial values for A, basically having obtained the initial values A1, A2 and B1, B2, C1, C2, we look at the initial values for D, E and F profiles. So I'm sorry. Okay, so first of all, for n equals 1, we see that there's no such new tiling which is possible here, because we can only place one square here, one square here and one square here. So those are the only possibilities so far. And yeah, so these are the 6 tilings, just in case. For n equal to 2, we can basically impose a profile A in behind the profile D, and that is because we have to prevent vertical faults. So what this exactly means is, suppose we have, I'll just illustrate with the profile D. So first up, let me just clean this up a bit. So suppose we have a profile D which is something like this, and this is the tiling of a 3x1 board. So we are basically tiling this board right here. So there is no other way than placing a square here. So there is only one possible tiling of the 3x1 strip, such that there is a D overhang. And similarly, if we have a 3x2 board to tile, so we have to tile like this, and there is a D overhang in the end, then in order to avoid a fault right here, because this is almost a fault, so in order to prevent that, we have to place a horizontal domino here. And then no matter what we do, we place squares here, or we place an entire vertical domino, we see that we have necessarily gotten a tiling of a 3x1 strip with an A overhang. So from this we can see that D2 is essentially just A1, which is 2. And from this intuition we can furthermore predict that any value of any dn would eventually become just an minus 1, because in order to prevent a vertical fault along this line, we have to place a domino here, and that is exactly an A profile, an A overhang profile at the previous line. So this is one thing. And similarly we can generate those identities for the other values as well. So these are the two tilings here and 4 tilings here. So we see that D2 equals 2 and D3 equals 4. Of course D1 equals 1, that is what we first discussed, and these are the similar things for E2, E3 and F2, F3, while D1, E1 and F1 are all equal to 1. So now we see that as mentioned, that Dn plus 1 is equal to An, En plus 1 is equal to Bn, and Fn plus 1 equals Cn for all n. That is because in order to prevent some vertical fault, we have to place the corresponding overhang before the D, E and F overhangs. So there is that. Now, okay, so that was just the background and setting up the stuff. Now we actually actively try to find a recursion. So to find a recursion, we start with the simplest example that we have, which is the example of the A overhang. So how does we just now look at how an A profile occurs? So that is basically saying what are the things that we can place right before it. So some things we can place right before it. Note that we cannot place two squares here. So if we place two squares here, there will be a vertical fault. So we have to place at least one domino. So depending on where the domino is, or if there are two dominoes instead of one, we get these three possibilities. So if there is one domino which is right next to the A overhang, it becomes a B profile with a square tucked on in the end. And if the domino is placed below, then it is a C profile, and if there are two dominoes, then it is of course a D profile. Note that we do not take into account the presence of this square here into the profile, because this square does not really generate a protruding profile or an overhang. It is just something artificially which has been tucked on. So the square is not really part of the overhang. It just can be placed or it can be removed, because it is just a square. It does not impose some rigid structure on the tiling, to put it that way. So from this we can see that for any tiling, for any overhang which is counted by an at the nth position, there has to be either a B overhang at the n-1 position. There has to be a B overhang or a C or a D overhang. So from this we can see that an plus 1 equals bn plus cn plus dn. There goes the first thing, and by similar arguments we can figure out these things, that bn plus 1 is also equal to an plus cn plus en, and along with these. So this is the first set of recursions that we have deduced about these tilings. Wait a second, I'll just demonstrate one thing, that bn plus 1 equals an plus cn plus en, if that might not be clear already. So yeah, suppose we have a B overhang somewhere, let's say like this, and this is the end of the board. Then we cannot place two squares here. This is not possible, because then we'll have a vertical fault. So okay, so in order to prevent that vertical fault, there has to be at least one domino right here. So depending on the position, if there is one domino here, and basically no matter what we do, it will become an A profile if there is exactly one domino here. If there are two dominoes here and here, then it is basically an E profile, as we've seen. So this is an E profile, and if there is one domino here and a bunch of squares here basically, then it is an A profile. As you can see, this is the A profile. So that explains this B, C and En terms. And if that domino which we see here is placed below and not above, then that becomes a C profile like this. So it will look something like this, let's say. So this is a C profile. So a B profile which ends at the nth position will necessarily be caused by either an A profile or a E profile or a C profile at the nth position. So that is that from that. And similarly you can work out how the Cn plus 1 comes from. And by substituting these recurrences and these values, we can get just a recurrence, three recurring relations in just A, B and C, the three sequences. So we have reduced the number of sequences that we are dealing with. We have reduced the complexity of the problem, and we have got three equations and three sequences to deal with. So it should lead to some deterministic value of a sequence, basically a recurrence of a sequence which is dependent only in on its own terms. So basically a recurrence for an only in terms of A, recurrence for bn only in terms of B, and recurrence for cn only in terms of C. So that is what we are up to right now, and that is exactly the lemma. We show that symmetrically all of these sequences an, bn and cn, they all follow the same recursion, which is 1 4 minus 1 minus 1. So they all follow the same recursion. It is not surprising that an and cn follow the same recursion, because they are after all just mirror images of each other. It takes a bit more of probably imagination and geometric argument to see that bn should also follow the same recursion, and that is because it is one of the more important things that we have done in our method. We have not at all looked at what is going on in the beginning of the tiling. So we have completely ignored how the tiling starts. We only look at how the tiling ends and what is going on near the end of the overhangs. So if we completely ignore the fact how the tiling starts, then the issues of horizontal faults and the position of B becomes more and more unclear, and we see that basically all the three rows become kind of independent, and so that is one very hand-wavy way of seeing how Bn should follow the same recursion. So anyway, that is what we can actually show. So we do not necessarily need to rely on the intuitions. So it is very simple, because we have to only manipulate these three equations. So from that we can see that an, bn and cn follow these recursions, follow the same recursion, 1 4 minus 1 minus 1. Okay, so now we can start actually looking forward to calculating Vn, which is in a way that we first get this recursion for Vn, which is we express Vn only in terms of an, bn and cn and its previous terms. So there's that, and something explains these coefficients here for 2n minus 1 and 2cn minus 1 as we will look ahead. So first of all, the first thing we get ourselves is this an minus 2, this bn minus 2, this cn minus 2. So we are not exactly very comfortable doing 2 steps before the tiling, basically two steps, let's put it that way, that we are not exactly able to determine from 2 steps ago what is the tiling going to be after 2 steps. But what we can do is, after given a step, we can look forward to the next step. So all in all, we basically want to bring all of these indices to n minus 1 instead of n minus 2. And the very simple way of doing it is replacing d for a and b for e and c for f. And so we get all of these terms with indices just being n minus 1. That is a bit easier, something to show. And this follows completely from geometric arguments. So so we suppose any vertically fault free tiling, and because there cannot be, let's see, suppose we have a vertically fault free tiling of this board, and because we cannot have because we cannot have 3 dominoes here like that, because that would generate a fault right here. It is necessary that we can have at most, we have to have at least 1 domino, because we cannot have a square here either, squares here, or basically just vertical dominoes. So we have to have at least 1 horizontal domino going right there. So depending on the number of horizontal dominoes on their position, so this is basically an A profile with some stuff added here, or if the domino was placed here, it would be a B profile, or it could be a D profile if there are 2 dominoes in the end which are placed like this, and so there has to be a square here and a domino here. So this is a D profile. So basically any vertically fault free tiling has to end in one of these profiles. So they have to end in either A, B, C, or E, F, D, F. Just to consider why there's a 2 in front of an, or an minus 1, we can see that if there's an A profile here, basically, whatever that be, then just below this overhang, we can have 1 vertical domino So that is one way of getting it. Or we can have two squares, so that is another way. So basically for any tiling of this board, so any tiling up to this, for any tiling up to this with an A profile, so basically whatever counts up to an minus 1, we can have two distinct tilings which ends this thing here, which is Vn. So that explains why there is this 2 in front of the an minus 1, because for any tiling or let's say for any vertical fault free tilings of this 3 cross n board, there are exactly two vertical fault free tilings of the 3 cross n minus 1 board, which ends with an overhang of the profile A. There is that, and so we can form these images right here. So this explains why there is this 2 in front of the A, that is the image, because for any vertical fault free tiling like this, there can be, if that ends with A, then there are two choices. And similarly for C there are similarly two choices, and for B there is exactly one choice, because the squares have to be like that. So that explains why there is the 2 in front of A and in front of Cn minus 1, and why all of the others just contribute 1, because they can only be completed by placing squares inside the profiles. So there is that. And using similar diagrams, so let's look at some similar diagrams. Let's say we have the board up to this, the board is up to this. Then let's say we have an E profile, so it has to look like this, and there is no other way than placing a square here. There has to be a square in this position, because placing a domino like this would cause a vertical fault right here, so we cannot do that. So that explains why exactly there is one way for the E profile. And similarly, if we just switch around these things, then it becomes exactly one way for the for the F profile, and switching these gives us exactly one way to complete the tiling for D profile. So there is that. So that shows our lemma, that Vn satisfies that recurrence. So just to have another look, this is the recurrence for Vn. So yeah, okay. Now basically having gotten the recurrence for Vn, we can just bring the formula for Vn, which is this, and we get also the first 6 values. So there's that. Just notice again that this recurrence for Vn also is the same recurrence, 1 4 minus 1 minus 1, and these are the first 6 values of Vn. And this is all done by simple manipulations of all the recurrences we have already obtained. So having these recurrences, that n equals an minus 1 plus 4n minus 2 minus an minus 3 minus an minus 4, we see that, and the all other analogs for Bn and Cn, and that Vn equals 2an minus 1 plus Bn minus 1 plus 2 Cn minus 1, and whatever the rest of it was. So basically plugging these into this formula properly, we can just get that Vn also is similarly equal to Vn minus 1 plus 4 Vn minus 2. So it is basically the same 1 4 minus 1 minus 1 thing again. It is just a matter of manipulation and dealing with all the things that we have already obtained. And this is the OEIS link for it, 335747, in case anyone wants to check out. So okay, that concludes this enumeration of the vertical fault free tilings. Now we look at the completely fault free tilings. So vertically fault free tilings which are also horizontally fault free, And this is rather simple because we have done most of the heavy lifting already here, and what we do next is basically based on what we discussed so far. So up to now, does anyone have any questions? Okay, great. So for completely fault-free tilings, let's just remind ourselves that we have obtained that u1 and u2 are both equal to 0, because it is not possible to have to avoid horizontal faults, and u3 and u4 equal to 2 by those two diagrams that we have seen before. And since un are always even numbers, we will be dealing with half of those values, and we see that to avoid horizontal faults, there have to be the vertical tiles which are placed like either like this or like this. So all of the tilings which are of this type, they have the analogs which are of that type, which are basically mirror images of each other. So that explains why un will always be an even number, because all of the tilings are basically mirrored. So we'll be looking at only the sequence Tn, which is half of un. So the Tn counts the number of tilings which are of this form, which have the vertical domino at the bottom left. So we just start dealing with the sequence Tn from now on. T1 equals T2 equals 0 because of this, and T3 and T4 are both equal to 1. From here we start out, and it is not very difficult as I said, because we have already done most of the stuff here. So as I mentioned before, for figuring out these recurrences, we only looked at what is going on near the end of the tiling, and we never talked about how the tiling began, really. So if let's say the tiling began with the configuration which is counted by Tn, let's say there is a vertical tile here and there is a horizontal tile like that there in the beginning, that is still counted by this A, and those things are still counted by the B, C, E, D, E, F profiles. So we can apply the same recursions on them. So that is exactly the point, that the recursion which we have worked out before, we can apply the same recursions on a new set of sequences which follow the same recurrence relations, and which probably have different initial values, but we can always count the initial values manually, so that helps us figure out the completely fault-free tilings very easily. So there is that. From this we can form these new six sequences in A-n through F-n, which are basically the number of completely fault-free tilings of a vertical tile, where we have a vertical tile on the bottom left. So where we have a vertical tile like this, these are completely fault-free tilings of this form, so such that there is an overhang of the corresponding profiles in the end. So okay, and because we do not really need to talk about how the tiling begins in order to figure out the recurrence relations, we just see that the recurrences just are the same, so nothing basically changes. And also, yeah, there is this important thing, that Tn is essentially equal to C dash n minus 1, and that comes from the fact that the end of the tiling looks like this. There is one horizontal tile here and there is a vertical tile here, and whatever comes here, we see that there is basically this C overhang right here at n minus 1th position. So whatever is counted by C dash of n minus 1, that corresponds exactly the same completion of the tiling which is counted by Tn. So that explains why Tn is equal to exactly C dash n minus 1. So we have basically figured out everything we need to know, and now we can just fill in some of the gaps, and namely those gaps are exactly the initial values. So we need to count the initial values, and then we have ourselves the recurrences that we can figure out for Tn. So what we need to do next is count the initial values of these three sequences. So initial values of a n, initial a dash n, initial values of b dash n, initial values of c dash n. And once we get ourselves a recurrence for c dash n, we automatically get a recurrence for tn, and from tn we can just double the values of tn. So basically tn and un follow the same recursion, and from that we basically have enumerated the completely fault-free tilings. So let's just get going with the initial values. So these are the initial values for a dash n, b dash n, and c dash n. We can see that a dash 1 is exactly possible because that fills in this prototype. So there is this vertical tile in the bottom, and above this there is the horizontal tile forming an A profile. And because this part is rigid and we have already filled out the 3x1 board, it is not possible to have profiles of type B and type C. So b-1 equals 0 and c-1 is also equal to 0, and a-1 is equal to 1. Similarly, in the next step, this image does not really do it much of justice, but yeah, you can see that a-2 has to be 0 because there is no way to extend this tile with an overhang right here, while also avoiding vertical faults and horizontal faults. So there is that. But we can fill in the gaps like this for b2 and c-2. So those two values are exactly 1. Let's just see again why a-2 equals 0, and that is because if suppose we already have started out with this kind of a configuration, so that forms an A profile right here, and this is how we have to start because we are counting the particular types which are counted by Tn. So in order to have an A hang over here, first of all, it is just not possible because for an A overhang we have to have a form like this, but we cannot place a horizontal domino right there. So at most we can do a square, but then in order to avoid a vertical fault right here, we have to have at least one domino which is placed like this, and that completely changes the profile because then it either becomes an E profile like this, or it becomes an F profile like this. So it is just not possible to have an A profile after for a 3x2 board. If we are tiling a 3x2 board like that, it is just not possible to end with an A profile. So that is why a-2 equals 0. And we have gotten ourselves two initial values each, and from this we can figure out some of the first values for Cn, which are 0 as in this 0, and then 1, and then next comes also 1, 5, 8, 26, etc. And also remembering that these are also the initial values for Tn, but except there is another T1 which is equal to 0. So this is basically T2, T3, T4, T5, T6 and T7. So we have gotten ourselves 7 initial values for Tn, starting with 0, 0, 1, 1, 5, 8, 26. We will be looking at what exactly these 5 and these 8 tilings look like. So that is basically something for the end. And we can crunch out the recurrences and see that Tn basically follows the same recurrence once again. So Tn also equals Tn minus 1 plus 4 Tn minus 2 minus Tn minus 3 minus Tn minus 4. That completely comes from these recursions right here, and the initial values that we get for ourselves. So it is somewhat incidental or coincidental that Tn follows the same recursion, and similarly because Un is just exactly 2 times Tn, Un also follows the same recursion. But yeah, it might not be just coincidence. So that leads us to the concluding theorem, which is if Un is the number of completely fault-free tilings of a 3x(n) board with dominoes and square, then here are the first 7 values of Un, which are 0, 0, 2, 2, 10, 16 and 52, and Un follows the same recursion 1, 4, minus 1, minus 1. And that is the sequence in the online encyclopedia for integer sequences. there is that, and some interesting facts, some weird facts up now. So this Tn, it is exactly the same sequence as something which I found named a Chebyshev related transform of Jakob-Stahl numbers, whatever that means, I have no idea. And also un and vn, they follow the same recursion, which is kind of not very unexpected, because they are after all dealing with the lack of faults. So both of these are vertical fault free tilings, and even though we introduce the fact that un cannot have horizontal faults, we see that the reason why un does not have horizontal faults lies exactly in how the tiling starts. So the fact that un does not have horizontal faults is exactly determined by this tile here and that tile in the end. So what goes on in the middle is completely the same thing as what is going on for Vn. So the process by which un goes to n plus 1, or let's say previous terms go to the next term of the sequence un, is the same process by which the previous terms of Vn go to the next term of Vn plus 1. So the process is the same, and the only things determining what is the outcome are these two dominoes which are placed here and here. Because in the middle we cannot have any vertical dominoes which place a wall like this. So everything here is basically horizontal dominoes and square. And if we just for a second ignore the fact that these terminal dominoes, these terminal vertical dominoes are here, the board basically breaks into three parts. So there are three horizontal faults which extend almost to the end, except they are stopped by these two dominoes. So that is kind of an explanation why un and vn follow the same recursion. But of course, these are not exactly very satisfactory explanations, because what exactly do I mean by the process? And even if the first domino does not affect the process, how can we guarantee that the last domino does not affect the process, and all those questions? But yeah, so there is that. And as promised, here are the tilings for T5, the completely fault-free tilings of the 3x5 board, with this particular configuration in the beginning. And taking the mirror image of all these, you can get the 10 tilings which are completely fault-free, and here are the 8 tilings which are completely fault-free with the 3x6 board. So we have seen, let's see, we have seen this guy before in the second slide or something like that, and these are the 8 slides here. And you can take the mirror images of all of these tilings to get the 16 tilings which are counted by U6. So I guess that is it. Does anyone have any questions? Or like anything which I failed to explain, or which was not clear enough, or anything, just if you got any questions. If not, then I guess we conclude this here.